It's a cold, moonless night with a mist that hangs heavy in the air. As you turn to cross the road, fog swallows both the sound and headlights of the oncoming car. You see it too late and brace yourself for impact. Then, out of nowhere, an elderly stranger shoves you out of harm's way, is hit by the car and ends up in a heap on the tarmac. Their life ends as yours is saved. Later, a police officer hands you an envelope found in the pocket of the deceased. It's addressed to you. You open the envelope and find a note with 2 words scribbled on it. It simply reads, "Study physics." Whoever wrote this note saved your life at the expense of theirs, so it only seems fair you follow their advice. Decades later you become a much celebrated physics professor. Your specialist subject? Albert Einstein's theories of relativity. You've always had a hunch that time travel is possible. Then one day, finally, you crack it and the world's very first time machine is sat, buzzing before you. Only then does the penny drop. How had you never realized before? You now have the power to go anywhere and anywhen, but you know exactly what you have to do. You take the letter you've kept all these years out of its frame on the wall, place it back inside its original envelope and put the envelope in your pocket. Stepping into your time machine, you set the controls to take you back to a cold, moonless misty night, arriving just in time to push your younger self out of the path of the onrushing car. You die on the roadside. Simple enough it seems. But the real joy of time travel stories like this one comes once you begin to scratch beneath the surface, and some incredibly profound questions begin to emerge. First of all, who wrote the letter? The older version of you simply takes the letter they'd already been given as a teenager back in time. The letter is a seemingly creatorless entity stuck in a time loop. This is the bootstrap paradox. Secondly, do those time loops keep on repeating? You save your teenage self, so they grow up to travel back in time to save their teenage self, who grows up to travel back in time and so on. You are stuck in a relentless cycle of living and dying, but the letter isn't. Does it just keep getting older and more worn and tattered? This is the restoration paradox. And whose idea was it to study physics anyway? The notion seems to appear out of nowhere, a thought with no origin. This is the ex nihilo paradox. If events like this can actually happen, then it also appears that you have no free will. No choices in life. You were always going to invent the time machine and had absolutely no option to do otherwise. It had to happen, had always happened. If you don't invent a time machine, then you can't save your teenage self, and you yourself would therefore die as a teenager. There is something in your future that's firmly fixed. This is called the predestination paradox. And finally, what if you change your mind? What if you decide not to trap yourself in the loop? Unfortunately for your older self, this is not an option. You can't get cold feet when you arrive and let the younger you get hit by the car. How could you be there to have second thoughts in the first place? This is the auto-infanticide paradox. It is seemingly impossible to kill a younger version of you, even through the act of not doing something. And so, not such a simple story. Welcome to the weird and wonderful world of time travel. But of course, traveling freely through time is impossible. You might say, you can't simply visit yesterday or rush headlong through millennia. And yet, this too is not quite so straightforward. Despite its myriad impracticalities, there are slivers of possibility lurking at the edge of physics, temporal loopholes lying just out of reach. And so, the question arises, if time travel is possible, just how could we do it? In 2021, a researcher at Portsmouth University calculated that there is about 6 by 10 to the power of 80 bits of information in the observable universe. Information is incredibly valuable, and data brokers are collecting yours all the time, and that is where Incogni comes in, our sponsor today. They reach out to data brokers and help take your data off the market. You see, your data is being sold online without you even knowing about it, and even though you can reach out personally and ask for it to be removed, it could take years to do it manually. Luckily, Incogni has a fully automated system to do it for you, protecting you from data breaches that are becoming more and more common. in 2021 alone they rose by 68%. Nobody likes being called or emailed by a stranger who knows your name and home address, so give Incogni a try to help protect your employment history, shopping habits, even the names of your relatives. This is the data these brokers collect, and if it leaks it leaves you at risk of fraud. So, protect your privacy by following the link in the description. The first 100 people to use the code UNIVERSE will get 60% off Incogni. Thanks to Incogni for supporting educational content on YouTube. In it, an advanced alien civilization reaches out to humanity with the design of a device capable of sending a single person across the vast chasm of space to the star Vega. Taking into account that nothing can go faster than light, this 25 light-year journey should take an achingly long time. So instead Sagan wants a way to get his heroine there far faster, but without invoking faster-than-light travel. Even though the book is finished, Sagan phones his friend Kip Thorne for advice. Sagan overnights the manuscript to Thorne, who reads it in the car the next day on his way to his daughter's graduation. A few quick calculations follow and Thorne has the answer. What Sagan needs in his story is a wormhole. Imagine spacetime as a sheet of paper with the Earth at one end and Vega at the other. Now instead of traveling the length of the paper, you fold the paper in half. After all, we know that spacetime can be curved and bent. Earth and Vega are now right on top of each other. Hop the gap between them and you get there in no time at all. From the outside it would look like you've got there by traveling faster than the speed of light, but at no point did you actually break through that sacred barrier. And so it follows that a wormhole can not only transport you to a different part of space, but it can also send you back in time. Let's say the wormhole to Vega is already set up. First you need to attach the Earth mouth of the wormhole to a rocket and drag it round on a loop through the universe at close to the speed of light. As the wormhole has been spending more of its spacetime budget on speed, less time will have elapsed from its perspective. So if you jump into the wormhole upon your return to Earth you will emerge at the other end in the past. Crucially, though, you will also be in the Vega star system. So it is backwards time travel, but not heading back into Earth's history. There is still a way to pull that off too, though. Set the wormhole up in the right way and the time difference between its mouths will be greater than the time it will take you to return to the Earth via the conventional route. You will arrive on Earth before you jumped into the wormhole in the first place. At least that's the theory. In practice it gets a little more complicated. Thorne realized that the gravitational pull of anything traveling through the wormhole will act to pull it shut. You would need something to help prop it open. This could be negative energy again, but physicists have also explored the possibility of using everything from quantum entanglement to magnetic fields. In 1985, J. Richard Gott and William Hiskek solved Einstein's equations for cosmic strings. 6 years later, Gott realizes that they could also be used as a time machine. Just like spiraling around a Tipler cylinder, take the right path along cosmic strings and you could end up tilting your light cone backwards. Quantum entanglement has also been mooted as another option. Physicists know how to link two particles in such a way that changing one instantly changes the other, even if you separate them by huge distances. It's as if the information about the change you've made has traveled between the particles faster than the speed of light. But it has turned out to be impossible to actually transfer data superluminally using this method. So it seems that there are multiple ways you might be able to travel backwards in time without breaking the light speed barrier, but were it to be possible, what could you do about the paradoxes? Quantum theory might offer a solution there too. Time streams, the handcuffs dig into your wrists and sweat streams down your face as you stare at the table in front you. On that table rests a glass vial of lethal gas next to a hammer on the end of a robotic arm connected to a machine that is constantly measuring subatomic particles. These particles can be in one of two states, A or B, and the chance of measuring each outcome is 50:50. It's effectively a convoluted coin toss. If the outcome of the measurement is A, nothing happens. But if it is B, the hammer falls, the vial is shattered and you die. The machine will make 100 measurements before the people watching from the other room will allow you to leave. Your odds of survival are around 1 in a million trillion trillion. You can feel your heart pounding in your chest as the machine makes its first measurement. You relax slightly, only to tense up again ahead of the next measurement a few seconds later. Again. After the 10th A in a row, you begin to feel hopeful. Surely you can't survive this. After 99 consecutive A's you're practically giddy. It all comes down to one final measurement. The machine clicks. Your captors are true to their word and unlock the handcuffs. You're free to go. Although you don't know it yet, your unlikely survival against seemingly impossible odds just provided possible proof of the many worlds interpretation of quantum theory, with potentially important consequences for resolving time travel paradoxes. This is a human version of the famous Schrödinger's cat thought experiment. The original imagined victim was a feline in a box with the same vial of poison and hammer. Quantum physics says that instead of being in state A or state B, the particle is initially in both state A and state B at the same time. Something physicists call a superposition of states. Except that means that the vial is also simultaneously unbroken and broken, and that the cat, and you, were both alive and dead until the point the next measurement is made. Is there something about actually making the measurement that forces the universe to finally choose one way or the other? Not according to the many worlds interpretation of quantum theory. Brainchild of physicist Hugh Everett III, it says that every time there's an event in the quantum world that has more than one outcome, all outcomes happen. At that point the universe fractures into two copies of itself, outcome A happens in one, outcome B in the other. Reality is constantly branching off to fashion a tree of possibilities. The great river of time bifurcates into infinitely many separate streams. There are some in which you were never born and others where you are president of the earth. If true, making 100 measurements with the poison and hammer machine would have created 100 different branches of reality. You died in 99 of them and survived in one. As the sole surviving copy of yourself, you marvel at your own luck. The 99 copies of you in the other branches, though, aren't so fortuitous, covering a sliding scale from those who died after one measurement to those who went through the whole process only to die on the 100th. This is known as the quantum immortality experiment. There will always be a version of you that stubbornly refuses to die no matter how many times the machine makes a measurement. It's a game of Russian roulette that you can never lose. While physicists do not know whether this interpretation of quantum physics is the right one, the many worlds theory could help us resolve many of the paradoxes often associated with time travel to the past. Take the most famous paradox of all, the grandfather paradox. You use your time machine to go back and murder your grandfather as a child. However, that means he never reaches adulthood, never meets your grandmother, and so your own mother is never born. If your own mother was never born, then you weren't either. How did you go back in time to murder your grandfather in the first place? Scientists, philosophers and writers have come up with various ways to circumvent this issue. Stephen Hawking introduced what he called the chronology protection conjecture. It states that backwards time travel is simply impossible. The universe acts to rob you of any opportunity to go back in time. Cause and effect are sacrosanct and tightly policed. Igor Novikov mused on something similar. His eponymous self-consistency principle says that you can go back in time, but you can't change what's already happened. If you revisit an earlier page in the book of the block universe, you cannot rewrite what is already written there. Attempt to murder your younger self and you will fail. Maybe the gun jams. Perhaps they sneeze and you miss. Try as you might, you could never succeed. But this of course raises other problems, whether events in your future are predetermined, or whether free will exists. Nor would Novikov's self-consistency principle work in all cases, as Barak Shoshani, Jared Wogan and Jacob Hauser show in a series of papers published between 2020 and 2022. Imagine you have a working time machine. You also have a set of balls that are either black or white. Crucially, when two balls meet, the encounter changes their color. So a black ball becomes white and a white ball becomes black. Let's say a black ball travels through the time machine where it whacks into its past self. This encounter changes both balls to white. The collision also knocks the ball that's already time traveled onto a path that eventually sends it back through the time machine a second time. In this scenario, the exact same ball exits the exact same time machine at the exact same moment in the past, and yet it is seemingly two different colors when it does so. This peculiar paradox cannot be explained away using Novikov's self-consistency principle. But, according to Shoshony, Wogan and Hauser, it can be explained using parallel time streams, the many worlds of quantum mechanics. They argue that time travel to the past is only possible if you emerge in a different stream from the one you left. So the black ball would start in time stream A, but would emerge from the time machine.